scientists have sort of a special way of looking at the world. I mean, everyone has their own unique way, but scientists have developed, I guess you'd say, a scientific way of looking at the world. And what is that? We call it the scientific method, and it's a way of learning about something that emphasizes observation and experimentation. What color? It's yellow. So observation and experimentation. We are different than philosophers. Philosophers sit around and think about stuff, right? And they reason things out, perhaps. A scientist is going to make observations. We're going to think about it then, but we're going to test our thoughts with experiments. So the scientific method is not a rigid procedure. It is not, okay, well, you do A, and then you do B, and then you do C. It's more of a general guideline or approach to studying something. And two people could apply the scientific method to the same problem and come up with different conclusions. It's important to understand that this is, our modern scientific method is very different from the Greek philosophers. I'm pointing in the wrong thing. I do that a lot. It's different from the Greek philosophers. They emphasized reason. Those were the guys that they sat around and they thought, and they argued and stuff, but they didn't actually do anything. So there's 4 key characteristics of the scientific method. Here's a flow chart. Some of you like flow charts, some of you hate them. I'll just throw them up here for those of you that like them. Can't really read these, they're too small for me. So starting point, we generally start with an observation. And from that observation, we're going to make a hypothesis. I'm going to explain all of these in more detail. The hypothesis needs to be tested by experiment. The experiment can confirm the hypothesis, or it could disprove the hypothesis. Then we would have to come up with a new hypothesis and test that again. Eventually, you go through this cycle several times, you get the hypothesis well confirmed, and that becomes a theory. There will be other people that will want to test your theory, and they'll test it with experiments and confirm or revise. Observations can also lead to laws, and laws can lead to hypotheses, and laws can be tested. And so there's this kind of interconnectedness of all these concepts. But the first thing is usually observation. Some observations you can make just with your eyes, naked or with contacts or glasses. Just looking at something, you can see what happens, or maybe you feel something. Other observations require instruments or powerful microscopes. You know, if you're looking at the temperature change, you're going to need a thermometer. That's going to give you a lot more information than just feeling it with your hand. But usually these observations involve a measurement of some kind or a description. Could be something to do with the color of it, but more typically it has to do with a measurement, a length, a mass, a temperature, things like that. An example of an observation that's given in your textbook is one made by Antoine Lavoisier. He lived back in the 1700s. I think it's helpful to talk about the experiments that were done in the olden days. I'm not going to test you on these. So we're just using them as examples. I'm not going to test you on who Antoine Lavoisier was and what were his ideas. But he studied the combustion of substances, burning things. He liked to burn things, and he burned them in closed containers, which is not something you usually do, right? But he would take, say, a small piece of wood in a sealed glass container and burn it and see what would happen. And he did this with other objects and other substances as well. And one of his observations was that when you burn something in a closed container, the mass of the contents didn't change. Now think about burning a log in the fireplace. So you pick up this log, and this is kind of heavy, right? You stick it in the fireplace, and you light the fire, and the log burns, and what's left? Ashes. Do the ashes weigh as much as the log did? No. What happened? Why does it weigh less? Well, the chemicals in the log were converted into gases and mostly went up the chimney. Lavoisier did his burning of things in a closed container where the products of the combustion couldn't leave. And so he would weigh this container with the substance in it, and then he would burn it, and then he would weigh it again, and it weighed the same. And that's a little bit surprising based on our observations of burning wood in an open fireplace, right? So this was an observation. Observations lead to the formation of a hypothesis. A hypothesis is a tentative explanation of the observation. We're trying to figure out why. Why is this observation? Why didn't the mass decrease like we see when we burn something in an open container? What's going on here? Some hypotheses are somewhat ridiculous, and others end up being correct. But it's just your best idea of what's going on. A good hypothesis needs to be, I didn't mean to do that. A good hypothesis needs to be falsifiable, meaning that you could test it and prove it wrong. So you want to come up with a hypothesis that you could test to see if it's right or not. So Lavoisier's hypothesis was that combustion involved the combination of the substance he was burning with some component of air. So it was combining with something in the air, and that's why the mass wasn't changing. Then the hypothesis is tested with an experiment. In an experiment, you need to control things. And one of the problems, like with learning about effects of diet and exercise and stuff on human health, is that humans are so varied and it's impossible to control everything. And so that makes things difficult. What I like about chemistry as opposed to biology is that it's inanimate things, it's non-living things, and you can control them for the most part. So it's important that it be highly controlled, and it needs to be designed in a way that's going to prove your hypothesis either true or false. So if your experiment shows that your hypothesis is wrong, then you have a choice. You can either just throw that hypothesis out, or you can tweak it. If you revise the hypothesis, then you test it again. And then this revising and testing and revising and testing goes on until you come up with a hypothesis that the experiment shows to be correct. Then you'll probably look at some other aspect of that hypothesis and do some sort of a different experiment on it. If we have a number of observations that have, let's start that sentence over. A number of observations can lead to what's called a scientific law. You're familiar with the law of gravity? So here's a dry erase marker. If I let go of this, what does the law of gravity say will happen? It falls to the floor. It does that every single time. That's so cool. Law of gravity. Does the law of gravity explain why the marker falls to the ground? No. It just says what is going to happen. Laws just say what happens. They do not explain why. In fact, scientists are still arguing and trying to figure out exactly what gravity is and how it works. They still do not fully understand that. So, a scientific law is a statement that summarizes what happens. It can be used to predict future observation. It's not that hard of a word. Future observations. So we can use the law of gravity to predict what will happen if I drop the eraser. It's going to fall, right? Sure enough, there it is on the floor. Works every time. Predicts the future. So Lavoisier, through his studies of burning stuff in closed containers, developed the law of conservation of mass that says in a chemical reaction, matter is not created or destroyed. That does not explain how that's happening or why. It just says what happens. In a chemical reaction, you're going to have the same mass that you're going to end up with the same mass that you started with. If you get one or more hypotheses, the hypothesis is trying to figure out why. One or more well-established hypotheses can lead to a scientific theory. The theory is explaining why. This provides an explanation for the observations and the laws. It's a model of the way nature is. So sometimes these are called models. We're going to talk about the kinetic molecular theory and the, what's one that's called a model? Mine went blank, I can't think of it. We're going to talk about some of these theories and models during the course of the semester. These theories often predict behavior way beyond what the original scientists expected. And so they help us to understand further. These are also subject to experimental testing. And sometimes, as new technology and new understanding comes about, we prove some of these theories to be incorrect, or we modify them. Going back to the example with Lavoisier, his law was that in a chemical reaction, matter is not created or destroyed. That led to, later in the 1800s, John Dalton coming up with his atomic theory. Atomic theory explains why matter is not created or destroyed, why the mass in that closed container is the same before and after burning the substance. John Dalton's theory explains why. So here's a comparison of law and theory. So the law says what happens, the theory tries to explain why it happens. The law arises from observations, theories arise from hypotheses. The law may prove to be false. A theory may also prove to be false, but a theory is as close to truth as we can get in science. One thing that's disturbing to some people is that we can't really prove anything to be true. We can only prove things to be false. So the things that we accept as truth, no one has been able to prove false. Now, at some point in the future, someone may figure out how to prove it false, and then that theory will be revised or changed. But we can't prove anything to be true. I should have been asking you guys for questions as we went along. Does anybody have any questions? You should always feel free to interrupt me if you have questions. Here's an example. Classify each statement as an observation, a law, or a theory. So this first one, when a metal is burned in a closed container, the mass of the container and its contents does not change. Is that an observation, a law, or a theory? That's an observation. Okay? It doesn't say why anything is happening. It's just saying what happens. So this is an observation. O for observation. Matter is made of atoms. I'm getting all three answers. Well, it can't be an observation because atoms are too small for us to see. And so this is not something we can observe. A law states what happens. A theory explains why. This would fall into the category of a theory, that matter is composed of atoms. Matter is conserved in chemical reactions. this would be a law. This is saying what happens. It's general. It's not applying to just one situation. It's general. Matter is conserved in chemical reactions, but it's not explaining why. So that's a law. When wood is burned in a closed container, its mass does not change. That's going to be an observation. Oops. Observation. Any questions? You should be able to take a statement on the order of this and classify it as a law, a theory, or an observation. Are atoms real? Well, for a long time, we had no way to get any sort of a visualization of atoms. This image is the Kanji characters, the Japanese characters for atom, written with individual iron atoms on a copper base. So these are pictures, if you will, of individual atoms. Now, this is not with a microscope, not with a regular microscope that uses light and magnifying lenses. This is with a scanning, tunneling microscope that uses electricity and a teeny tiny probe and very sophisticated electronics to give us this computer-generated image of the atoms. But this is as close as we can get to getting a picture of an atom. But if you look in different textbooks, you know, they've done different little atomic sculptures out of these. One of them said, do your homework. One of them says IBM. Apparently they worked for IBM. I like this one personally.